All right, in the last video, we graphed polar equations and learned a little bit about how a polar coordinate axis works. In this video, we're going to break down a polar graph into x and y components. We're going to use those x and y components then to look at the derivative and what the derivative tells us. So just as a review, because we're going to be using r equals 3 sine theta quite a bit in this video, why don't you take a moment and graph this? Pause this and graph. Okay, I'm not going to take too much time explaining it again, but I'm going to just quickly graph the rectangular version of 3 sine theta. So I know that this is 0 to pi. I know that pi is an important value. Pi over 2 is important. And 3 pi over 2 is important. Okay, since we know that this is not being stretched horizontally, I do know, however, this is being stretched vertically. So that just means instead of going up to 1, this will go up to 3. So we know 0, 0. We know pi over 2 is normally 1, but because we're stretching this by 3, that's now up at 3. Pi is back to 0. 3 pi over 2 is down to -3 then, and 2 pi is back to 0 again. All right, if we graph this, the point 0, 0 is here in the center. Pi over 2 is up to 3. So I'm going to connect this. Pi is back to 0 again. I'm going to put some direction here. And then 3 pi over 2 is -3. So that's just going in circles. So we completed one complete cycle by the time we reached pi. So the period for this is pi, something we'll have to remember. 0 to pi is one complete cycle for this graph r equals 3 sine theta. All right, we talked about this a little bit in the last video. This r value is the hypotenuse, if you will, because we've talked about this, that these values are coming from the unit circle. So using this triangle from the unit circle, we can write some relationships. So for example, we know that the sine of theta equals the opposite over the hypotenuse. And if we isolate y, we know that y is equal to r times the sine of theta. That's something we're going to use here in just a few moments. If we look at the relationship between cosine of theta and the sides of this triangle, it's adjacent over hypotenuse. So x is equal to r times the cosine of theta. Also something we're going to use. These two are pretty important, and we'll come back to those in a minute, but let's just finish looking at some of the other relationships. Looking at tangent then, I know that the tangent of theta is opposite over adjacent. Good to know, but trying to isolate y just gives us y equals x tangent theta. Not as interesting because it's not relating, it's not relating that r value that we had. Wow, sorry about that little blast from the past. Because r is the polar graph that we have, the polar equation is r equals 3 sine theta. So that's going to come in handy. And one last relationship, if we use the Pythagorean theorem, x squared plus y squared is equal to r squared. Okay, now we're going to use what I told you before, the y and the x. Those are called parametric equations. Parametric equations means we're writing x and y as a function of a completely different variable, of a parameter, and in this case the parameter is theta. So we're writing the value of x and y as a function of theta. So what is the value of x at different values of theta? And what is the value of y at different values of theta? So what that does is it allows us to look at the x separately from the y. So eventually we're going to look at how is x changing as theta is changing, and how is y changing as theta is changing. Those are called parametric equations. So we're going to write r equals 3 sine theta in parametric form. Okay, so if I'm going to write r equals 3 sine theta in parametric form, I'm saying what is the x going to be as a function of theta? So we'll just write it as x of theta. And what is y going to look like as a function of theta? So as y of theta. All right, so let's plug some things in that we know. We know that x is equal to r times the cosine of theta. Well, in our case, r is 3 sine theta and then times cosine theta. If we look at y is r times the sine of theta. In this case, r is 3 sine theta and multiply by the sine of theta. Let's simplify that just a little bit more. 3 sine squared. Okay, but what do we do with that? So let's look at a non-calculus way to look at this. And it's not super useful because we've already graphed this using x and y, but I just want to show you what's going on here. I'm not going to do too much with this. I'm just going to kind of get it started just to show you kind of how things are shaking out. So what we can do is create this big table of values, and this table of values is going to be a little different than what we're used to because we have this third parameter. Theta is determining what is x and what is y. Well, we know that, I'm going to turn my iPad sideways so that it's not, there we go. So we know that x of theta is 3 sine theta cosine theta, and y of theta is 3 sine squared. So we're going to use that to find the x and the y coordinates. Just bear with me for a minute. So we're saying let's choose a value. Let's choose 0 for theta. And let's plug that in here. So if we have x of 0, 3 sine 0 cosine 0. Well, I know that the sine of 0 is 0, so this entire thing is 0. And y of 0 is 3 times the sine squared of 0. Still sine is 0, so that's 0. So we're saying at the angle 0, the x is 0 and the y is 0. Let's go look at the graph that we did before. When the angle is 0, so here's theta, we're saying move 0 to the left and 0 up and down. And we did that already. We've got 0, 0. Okay, great. This seems like a lot of work for nothing, but let's just keep going. If I look at the angle pi over 2, x of pi over 2 is 3 sine pi over 2 times the cosine of pi over 2. Well, I know the cosine of pi over 2 is 0, so this becomes 0. Y of pi over 2, 3 times sine squared of pi over 2. Well, the sine of pi over 2 is 1. 1 squared is 1 times 3 is 3. So now we're saying when theta is pi over 2, x is 0, y is 3. Let's go take a look. When theta is pi over 2, so here's our pi over 2, x is 0, so we don't move left or right, but y is 3, and that put us up at this point right there. And so on and so forth. That's not really the most useful application of parametric equations, but I just wanted you to see how this is working, that angle is kind of telling us what x is doing and what y is doing at that moment in time. Speaking of that moment in time, let's start talking about the derivative. Let's use these parametric equations to look at tangent lines to this polar graph. So we're going to move down now. We're going to determine the location of horizontal and vertical tangent lines to that polar graph, r equals 3 sine theta. Now, some of them are easy to see from the graph, but some of them are not quite so easy. So first of all, let's look at horizontal tangent lines. So horizontal tangent lines occur when the slope is equal to 0. So horizontal tangent lines occur when dy over dx is equal to 0. The way to make a fraction equal 0 is if the numerator is equal to 0. So this happens when dy is equal to 0. Well, in our case, because we're looking at this r sine 3 sine theta, we need to know dy. We need to know how y is changing. We have an equation for y. Y was 3 sine squared theta. So in order to find dy, we find that derivative. Okay, I'm going to use the chain rule, so I'll multiply 2 times 3, that's 6, without changing the inner function, multiplied by the derivative of the inner function. That's what we've got. Okay, so we're looking at horizontal tangents. We need to know when the change in y is 0. Since we broke down r equals 3 sine theta into x and y, we can find that. All right, so here's y prime. Let's set that equal to 0. So we know, since this is multiplication, whenever sine of theta is equal to 0, this whole numerator will equal to 0, or when cosine of theta is equal to 0. Now let's keep in mind that the period of 3 sine theta is just pi. So we're only looking from 0 to pi. All right, so sine theta is equal to 0 at 0 and pi. Cosine of theta is equal to 0 at pi over 2 and 3 pi over 2. But 3 pi over 2 is outside of our domain here. So just 0 pi and pi over 2. That's where we have horizontal tangent lines. We could have seen that up above in our graph. We've got horizontal tangent lines here and here. That happens at 0, pi over 2, and pi. Now the tricky part is, where do these vertical tangent lines occur? So let's go see if we can find those. Okay, let's find the vertical tangent lines. Similarly, vertical tangent lines occur when the denominator is equal to 0, so when this derivative is undefined. That happens when dx is equal to 0. Why don't you pause and see if you can solve that to find dx and find where dx is equal to 0. And just as a reminder, x was 3 sine theta cosine theta. So go find that derivative, see if you can set that equal to 0, and see what you can find. Okay, I hope you actually tried. Let's find x prime. I'm going to use the product rule. So 3 times the sine of theta, the derivative of sine is cosine, so this is 3 cosine theta times cosine theta without changing it, plus 3 sine theta times the derivative of cosine, so that's negative sine theta. If I simplify this, I have 3 cosine squared theta minus 3 sine squared theta. And I'm trying to find where this is equal to 0. I'm going to divide out the 3 just to make this easier because it's just a constant. So I end up with cosine squared theta minus sine squared theta. All right, I can factor that because that's a difference of squares. Cosine theta plus sine theta times cosine theta minus sine theta. Okay, now that I've factored that, I can set each of those factors equal to 0. Where is cosine theta plus sine theta equals 0? And where is cosine theta minus sine theta equals 0? Okay, so I've got 2 different things that I'm looking at. Where is cosine the opposite of sine? And where is cosine equal to sine? Now remember, we're only looking on the unit circle between 0 and pi, so we're really only looking at the top two quadrants, quadrant 1, quadrant 2. Well, I know that cosine is equal to sine when they're both root 2 over 2, and that happens at pi over 4. Where are they the same but just different in sign? That's at 3 pi over 4. They're both, cosine is negative root 2 over 2, sine is positive root 2 over 2. So we've got 2 different angles. So when we look back up at the graph, so these are the 2 angles where we have vertical tangent lines. Those vertical tangent lines occurred here, and if my graph was a little bit better. but pi over 4 it would be about right there. That's about pi over 4. And about 3 pi over 4. I'm not saying it falls right on that concentric circle. I'd have to do some solving to figure that out. But at least at those angles is what we know. Okay, that was kind of the derivative of, or the beginning of the calculus of it all. Tomorrow and the next day, the next lesson, you're going to learn about how to find the area of these polar